Sure might do. Okay, so we have 2010 U-values question here. I've drawn the wall, okay, outside and inside. We've drawn in all our materials, and we're going to now do our table for part A of the question. All right, so part A of the question is here, asking us so we have our materials here and the thicknesses of them, okay. Remember, when you're doing your thicknesses, you must show the materials, the thickness of them in meters. So you'll see I'll put a little M there above my thickness, all right. So we'll write in the list of materials that we have. So the first one is the ESR, which stands for external surface resistance, which is the pocket of air on the outside. Okay, the resistance value for that we were already given, so we're given value or, large or, goes in here, 0.048 meters squared degrees Celsius per watts. Okay, the next product that we have working from outside to inside, because that's where the cold or heat loss is going to be traveling, we have our external render. Now our external render is given as a thickness of 12 millimeters. What is that in meters? So if we're unsure, we take 12, we divide it by 1,000, okay, and you get your thickness. So it's 0.012. Is that all right? So everything is in meters, so there's 1,000 millimeters in a meter. That's why we divide by 1,000. Now, the value for the external render is in the K category, is the conductivity, and that's 1.430. I'm going to work on these resistances in a minute. I'm just going to fill in my table first, okay? The next thing I'm going to put in is the concrete blocks. So we have the next concrete block is the exterior concrete block. Okay, its thickness is 100 millimeters. Sorry, I forgot the 0.012, wasn't it? Is 0.1 of a meter. The conductivity value that's given to me for the concrete block is 1.440. Then I have a cavity, okay, and the cavity is 150 millimeters. So we'll say cavity, which is 0.15. The conductivity of that cavity is 0.170. We have our insulation, which goes into the cavity, okay, and its thickness is 0.1 as well, and the conductivity value for the insulation is 0.018. Then we have our internal concrete block. This is why we draw it, because if I was going by the information given to me in the table, I would forget about that internal block, because I might forget about it. So by drawing it, we can tick off our list, knowing what products we have. So the internal concrete block is 0.1 in thickness, and its value is the same as above. Okay. Then we have our internal plaster, which is a thickness of 0.015, and its conductivity is 0.430. And then we have ISR, which is the internal pocket of air, which is the internal pocket resistance, and it's given over here of 0.122. Is everybody happy with that? Now, how do we get our resistance values in here? Very simply. The formula is as follows. T over K equals R if you are given the K value, and it's T by small r equals large R if you're given this small r value. Okay, you need both of them because sometimes we can give them both of them in the question. In this scenario, we just happen to be given the conductivity, but it's worth noting that information. Is that all right? Now, we'll take our calculator to do these. Okay. Can you see it? No. Okay. So we're working with T over K at all times. So it's 0.012 divided by 1.430 equals 0.008. And I'm just going to work to 3 decimal places. But stay consistent, is that okay? Either work to 4 decimal places at all times or work to 3 decimal places at all times. Whatever you're doing, just keep consistent. 3 decimal places were provided to me already, so I'll go with them. Do you know where they are? There's one over there. And then check those drawers, please. Okay, then the next one is 0.1 divided by 1.440. How are we? Gives us 0.07. Or 69. I said I was going to work to 3 decimal places. Have you got this done?
Yeah, I'm doing it.
Well, get going. You should be ahead of me.
There's one here as well.
Okay. Is it? Oh, good spot. Thank you. Brilliant. Thanks for that. Yeah. So the cavity, the value for the cavity, guys, was the resistance value, was the large ore. Thank you very much for that. This is why we double check things, I suppose. Okay. Now, the value for the exterior concrete block is going to be the same for the interior block, so I might as well put that value in there as well. Now, insulation. 0.1 divided by 0.018. Giving me 5.556. Is that all right? Yeah, do we all understand that? You can see it on the calculator, so I'm rounding up to 3 decimal places. And then the interior plaster is 0.015 divided by 0.430 equals 0.035. Rightio. Now, so that's all my resistance values, yes? And so what I need to do now is find my ore total. So we add all of these up. To get our ore total. So 0.048 plus 0.008 plus 0.069 plus 0.170 plus 5.556 plus 0.069 plus 0.035 plus 0.122. How do I get rid of that? Anyway, I have an extra 2 by accident, but anyway. I presume the value, guys, then is 6.1992. Would that be right? I put in an extra 2 here because the calculator banjaxed. Let me try that again.
Do you want to use my calculator?
No, it's okay. 0.048 plus 0.008 plus 0.069 plus 0.170 plus 5.556 plus 0.069 plus 0.035 plus 0.122. 6.077. Yep. Brilliant. Now, just going to go like that. Now, for our U value equals 1 over RT. RT stands for ore total, yes? So I put 1 over 6.077. Take my calculator again. We go 1 divided by 6.077. 1 divided by 6.077 equals 1.165. Is that correct? And that's meters squared degrees Celsius per watt. That is our current U value. Everybody understand that? That's easy, yes? Okay, good. Now, we have to use that value in part B. So that's part A. I will come back, guys, and what I'm going to do is I'm going to change that value. So I'm going to say that this question was 2010. I'm going to introduce new modern standards. I'm going to ask you, I want you to update, renovate, okay, or retrofit that wall to make it up to today's standards. I want you to add insulation to it to make it up to modern day standards. How much insulation do we need? Does that make sense? Yes? I'll come back to that. I'll add that in as part D of the question. Okay, so we have our U value. Now we're going to go to our heat loss. So this is part B of the question. Now this is where a lot of us try to cut corners and it doesn't exactly pay off. So now, what is the first formula? So, sorry, we'll go back to our table here. I'll just scroll down a little bit so we can get our values here. So part B of the question says, using the thermal data below and the U value obtained at 5A, above, calculate the cost of the heat loss annually through the walls of a new house specified at 5A and a house built in the 1970s with an external wall U value of 1.8. So you actually have to do this twice. You understand? Okay. Now, if we were doing that, what would today's external wall U value be? Does anybody know? 0.015. What is it? 0.015. I think it's 0.15. I think. Is it? Yeah. I think it's 0.15. I could be incorrect on that, but you can see that the 1970s wall has a really high value, 1.8. The wall we're after calculating is probably the walls that's in all of our houses, which is relatively warm, yeah? And we got a value of, what is it, 0.165? Yeah? And in today's standards, the NZ standards is 0.15, so we're lowering it again. Is that alright? So you might be asked for that in the question. So if we can do that twice, we're going to do it twice. Now, the key information here for this is the external wall is 152 meters squared. We have an internal and external temperature, 17 degrees and 6 degrees. The U value of the wall calculated at 5A, U value of 1970s wall. The heating period is 11 hours a day for 41 weeks, which means it's on 7 days a week. And you need to know that, okay? Per annum means per year. It's 65 cents per litre. I wish it was back to that value again. The calorific value of the oil, of a litre of oil, gives you that. So you can imagine when you eat a chocolate bar, there's a certain amount of calories in a chocolate bar, a certain amount of energy produced or heat produced. When you produce, or when you burn your litre of oil, that's how much energy is produced. Okay, so you need to eat a lot of chocolate bars for that. And for every 1,000 watts, it's 1 kilojoule. Okay, which is also important, so we have to calculate that. So, we've all that information. And there's a stepped process to this, and I'd like you to follow the stepped process and try not to cut corners, just for simplicity, just so that you don't get anything wrong. Is that okay? So for our general heat loss, what we first off have to do is we have to take our U value, we multiply it by the temperature difference, multiply it by, what is it? Yes, sorry, by the area. Sorry, I did these the other way around. I was thinking in my head. So the temperature difference multiplied by the area. So first off, what's our U value for our, so this is part 1 of the question. So this is question part B, but it's the first part. This is also another thing that you're bad at, labeling your questions. Okay? So this is question 5, part B, part 1. Okay? So we have our U value. which is 0.165 multiplied by temperature difference. Outside is 17 degrees, inside is 16 degrees. What's the temperature difference? 11. The area is 152 meters squared, isn't it? So very simply, we take our calculator, 0.165 multiplied by 11 multiplied by 152 gives us 275.88. Now that's in watts. Okay? The next thing that we're going to do is we are going to calculate then the seconds and how long the heat is on for. So, you have to do this in seconds. Is that all right? So we'll just put it in seconds. So, there are 60 seconds in a minute. There are 60 minutes in an hour. How many hours is the heat on for? 11. How many days in the week? And how many weeks of the year? So, that will give us our value in seconds. So we take our calculator again. We go 60 times 60 times 11 times 7 times 41 equals 1136520 seconds. We all understand that? Yes? Okay, good. Now what we're going to do is we're going to take the amount of time and the amount of heat loss and multiply them together, and we're putting it over 1000 because we want to convert the watts to kilojoules. So we'll take these two values, we'll multiply them together. So we'll go 1136520 multiplied by 275.88. That's watts, and that's our seconds, over 1000, because we want to convert it to kilojoules, okay, or convert it away from kilojoules. So again, we take that value, multiply that by 275.88 equals 3. Let me try this one more time just to make sure. Was that, let me just do that again. 60 seconds times 60 minutes times 11 hours times 7 days times 41 weeks. Yes, you're right. Sorry, thank you, Paul. Good man. So multiply that by 275.88. Three 65200 multiplied by 1136520 multiplied by 275.88. What's the value you've got, guys? For that, because my calculator's just coming up a bit strange. Yeah, okay, so I'll do it again. So 1136520 multiplied by 275.88. 313543136 kilojoules per second. Is that okay? Now, as I said to these guys, I know some of you are cutting corners and stuff like that, but I would like you to break it down like this so that you don't make any mistakes, because you were making mistakes in the Christmas exams, and I'd like to avoid that. So now we know how many kilojoules it requires for the year for that wall. Yeah? Now we need to know how many litres of oil do I need to burn to create those amount of kilojoules? Yeah? and it tells us the value of the kilojoules of the 1 litre of oil. So I'm going to take this value then, and I'm going to divide it by 37350, because that's what 1 litre of oil burns. Does everybody understand that? So we take that value, we'll go 313537376. My calculator's run out of digits. So maybe don't invest in a as cheap a one as that, maybe, guys. Remember I was telling you to divide or to get a cheap calculator. 37350 equals 83947, is it? Let me try that one more time. So we go 313543136 divided by 37350 equals 83947. No, we're doing that right now. Did anybody else get that figure? What did you get, Rain? She didn't do it. Or did you? You did do it. What did you get? What? You got that? Fiona, what did you get?
Yeah, 83.69.
Why is mine? So what did you get for the kilojoules then up here?
Kilojoules, 312593.
Okay, what did you get for the watts? Yeah, see that's different. So 0.165.
Yeah, for my U value, I done 1645.
Okay. Okay. Multiply by 11365200 equals divided by 1000. 3135431. Ah, this is 0.376. That's why. Divided by 37350. There we go. I was wondering where I was wrong. So 83 litres. Sorry, I just had to put it into my calculator again, but it was 83.947 litres. How much does a litre cost? So 65 cents. You can see what I'm doing. Sorry, it just doesn't run off the screen. You can still see what I'm doing. Okay. And by 65 cents, so multiply that by 0.65, and you get €54.57. Does that make sense? Do you have to do that again? Yes, we do. We have to do it again for the next wall, don't we? Okay. So, have you done that? Okay, so we're going to do this again for the second part of this. So this is part B, but the second value for the 1970s house, isn't it? The 1970s U value is 1.80. Okay? So we're going to do the same thing again, but now for the second house, okay? Which is not hard now, guys. It's really not hard. It's just doubling your workload. That's all it is, okay? So we're taking 1.80, multiply it by 11 degrees Celsius. That's the temperature difference. Multiply it by the area, 152. Your value for this then is 1.80 multiplied by 11 multiplied by 152 gives you 30096. Sorry, 9.6 watts. Then we're going to do our seconds for the time of heat loss. Obviously, you don't have to write out these words. I'm just doing it to clarify what we're doing. So it's 60 seconds by 60 minutes by 11 hours by 7 days in a week by 41. That's going to be the same value as the previously, isn't it? Yeah? So it's going to be 11365,200 seconds. Is that all right? And then we're going to go and we're going to multiply the two values together. And we put it over 1,000 to convert it to kilojoules. So 11365,200 multiplied by 309.6 watts all over 1,000. Okay, and that value then gives us, my calculator just doesn't have enough screen on it to work, so I'm going to do it on my phone. 11365,200 multiplied by 3009.6 divided by 1,000 equals 342,04705.92 kilojoules. Okay, am I right so far? Is everybody with me? Yeah? Okay. And then we're going to take that and we're going to put it over the calorific value of a litre of oil. So then you're going to take that 342,04705.92 divided by 37350, giving us 915.79 litres of oil that we need, which is an awful lot, as you can see, in comparison to our other house, our current building house, that we probably live in ourselves at the minute. 2010 regulations, probably the same as what yours are living in. Then we multiply that by the cost of oil, which is 0.65 litres, sorry, 0.65 euros. So we multiply that by 0.65, giving us €595.26. That's how much it costs to heat one wall in a 1970s house. €595 a year for one wall in a 1970s house. That alone tells you how it is beneficial to have a better insulated and higher heat and efficiency house, doesn't it? You'd be at an absolute fortune. How many walls are in your house? You know what I mean? 4 walls, that's 2,000 a year, plus the other walls that and other materials that are wasting away. Okay? So that's that. The other element that I was going to add in, okay, is I would like us to change. So I want us all to do this now, please. Okay? Is I want us to take this table. All right? I want you to put in another piece of insulation, and the end value I want it to be is 0.15. So the phrasing of this question is, how much insulation is required to add to that wall to meet 2024 standards of 0.15 U value? Is that okay? You understand that? So we get our next page and we'll say how much insulation is required to meet U value of 0.15 meters squared degrees Celsius per watts. Okay? Do you understand that? So that's what I'm asking you to do. So I want you to redo that table, but I want you to add in a new material, which is insulation. It's the same type of insulation, so you already have the conductivity value of it. The thing is, we're trying to find out how thick the new piece of insulation is going to be. All right? And again, for this, just for clarity purposes, again, so that we're understanding what we have to do, I'm going to draw the wall. I'm going to take my exterior, now we're trying to find the thickness that I need, of insulation that I need to add to the house. Now if you're doing this, you could add it to your inside walls. If it's a retrofit house, you could get a grant, maybe you could put external insulation on the outside of the house, like you would have seen that time we visited Core. So we have, depending on where you want to put it, I'm going to put it on the inside just because it's easier to do. So we'll have our concrete block, we'll have our cavity which has a fill of insulation in it, we'll have another concrete block, and we'll have our internal plaster. So our hatching identifies that this is concrete, this is concrete. I have my insulation coming down the middle. This was our previous house. And what I need to do now is I need to add insulation here. So I'm going to do this in blue just so it's highlighted. I'm going to have to add insulation here to our inside wall. How much? I don't know. There's also then going to be an internal plaster. The same number of internal plaster is going to be applied, and then we're going to have the same ISR on the inside as well. Okay, just so you have an idea of what we're doing, okay? So, how much is this, how thick is this insulation essentially going in here? Does that make sense? So, that's what we need to figure out. So, I'm going to redraw the table, put in most of my information, but just leave out one little section, and I'll work backwards to get my thickness. So we put in material, put in thickness in meters, we put in conductivity, K value, resistivity, small r value, resistance. Remember guys, there's no point just copying me either. You're going to have to do this for yourself at some stage, so get your confidence up now, okay? And I do advise that you do a few practice ones of these for your revision for your mocks, okay? Each question you should be allowing roughly around 30 minutes to do. This one should definitely be less than that, all right? So our materials are ESR, external render, we've external concrete block, we have a cavity, we have insulation that's already inside the wall, we have our internal concrete block, we have then we're going to have internal plaster or new insulation, new insulation, okay? Then we're going to have our internal plaster that's going to be the same. And then we're going to have ISR. So this here is our new product. And this here is the value we're looking for. We're looking for the thickness. So all the other values will be the same. ESR is 0.048, 0.008, 0.012, 1.430, 0.1, 0.15, 0.1, 0.1. ISR value is 0.122. Internal plaster value is 0.035, 0.430, 0.015. Internal concrete block is 1.440, 1.440, and 0.018. This value then is 0.069, 0.069. Cavity is 0.170. Insulation is really high value of 5.556. So the line of the new insulation is the thing that I don't know. The only thing I do know about it is the conductivity value, because it's the same type of insulation that I'm putting in. Does that make sense? Whether it's rock wool, whether it's rigid insulation, I'm going to use the exact same type. So whatever my local hardware provides, I'm going to use the exact same again.
Are you going to select what kind of size the insulation is?
I have to find out, because I want to get up to modern day standards. So, like, Dominicus is doing this in his project, right? So we could pump the walls, all right? That's a way that we can further insulate our house. Or we can put external insulation on it, or we can put internal insulation on it. But I want to make it warmer. So the current value for a wall is 0.15 meter squared per degree Celsius watts, right? So that's the value. So I have to meet that value. So I have to make my wall meet that value. So it's currently at 0.165. I need to reduce it. So I need to add insulation, but how much do I need to get to that value? Does that make sense? And it mightn't be a nice round number. So if I add more than that, then I'm going to get a lower value, which is going to be better. Does that make sense?
Exactly 0.5.
So I'm putting in exactly 0.5. Yeah. Okay? So how does this work? So we know then the values for us are changed. Our total value is going to change because we have a figure in here that we have to put in. And our U value is now changed from what it was. Our U value is 1 over RT, which is equal to 0.15. Now we have to work backwards. Okay? So, we have 0.15. To work backwards, all you have to do is put 1 over that value, and it will find you what the R total is. So to find the R total, 1 over 0.15 will find it for you. So if I take my calculator, and I take 1 divided by 0.15, I get 6.667. Is that all right? Now, that's my new R total. I can take away my old R total to find me the value that goes in there. And my old R total was 6.077. So if I do that, minus 6.077, that gives me the value that I put in here. 0.589. Do we understand that? That's my new value that I found by taking the R total of my new wall and taking away the old R total from it. Do we all understand that? So I got 6.667 and I minused 6.077 equals 0.589, and I put it up there. Now I have 2 of my 3 pieces of information for my equation here to find the thickness. What is my equation? My equation is T over K equals R. Let's put in the values. For R is 0.589. T, we're still looking for, over 0.018. Yeah? Is with me? So now to find T, if I take this figure and put it across the equal symbol, what happens at Paul, mastermind of maths? When it's a division and it goes across, it becomes a multiplier. So therefore T equals 0.018 multiplied by 0.589. I'm have to delete my course. So 0.018 multiplied by 0.589, giving us 0.0106. That is in what? What unit is that in? Meters. What are we gonna, if I'm going into a shop to buy it, am I gonna be providing the meters value? Or what would, sorry, I'll ask you this. What was at the top of the question, what was the measurements given to us in? It was given to us in millimeters, so I'm going to convert that to millimeters. And what's 0.01 converted into millimeters? What is it? Not 100? 10. Yeah, throw them in the brown drawer over there, please. So that's equal to 10 millimeters. That's all we need. Yeah? Any more than that, no worries, any more than that is going to give us a value that is better or lower than 0.15. So if I added more insulation to that, it's going to give us something, a better value.